morning again, everybody. After that snazzy introduction, I wanted to introduce you to one more person who's as cool as the video that we just saw, and he is continuing the trend of marketing since morning. I would like to welcome Mr. Yousef Khalilollahi, who's the Vice President of Core Vertical Markets at Xilinx. He's got about 20 plus years of experience. He's been with companies such as Acronix, LSI Logics, and Actel Corporation before this. He's got a master's and bachelor's in science and electrical engineering from University of South Carolina, and Southern California. And what we would like to hear from you, Yousef, is since you're handling FPGA, structured ASICs, and the ASIC market, is how do you think we here can play a role in adding value to the country by leveraging your products? I'm hoping you're going to touch that. The Makeathon was specifically a cue for you to talk about how the products can be used within the Makeathon space. Thank you. Over to you, Yousef.
Thank you very much for that introduction. It's the first time I've been referred to as cool, so that's very exciting for me. So that's good. Again, my name is Yousef Khalilollahi. I'm responsible for Xilinx's business in a collection of markets that includes aerospace and defense. I am based in San Jose, California in the US, and it's a privilege for me to be invited to this event to deliver the keynote. I definitely appreciate your attention, and thank you very much. So I'm going to cover a number of topics that hopefully addresses some of the questions that you brought up. I'll start with the general market dynamics of the global aerospace and defense market. I'll talk about some of the application trends, and specifically I'm going to talk about big data, AI, artificial intelligence, and machine learning. Those are kind of the buzzwords that you hear in the commercial world. So I will talk about how those apply to aerospace and defense from our perspective and our advantage view. And then also, toward the end, I'll talk about some of the issues that the industry faces in regards to supply chain, end of life, and life cycle management, and where Xilinx is focused to address all of these applications. So when we talk about aerospace and defense market, I always like to start with one of the key drivers in driving the global aerospace and defense market is the global defense budget. So this chart here shows you the 2017 defense budget spending across the world, and it shows the top 15 countries. At that very high level, the global defense budget over the last couple of years has gone from flat to down to increasing. As you can see in this chart, the global defense budget rose about over 3% last year. That may not seem much, but it was declining for many years before that. And all in all, of the top 15 countries that you see here, 13 of them increased defense spending in 2017 versus 2016. Now, of course, the US dominates the global defense spending. About 35% of the defense spending is in the US. But it's very much worth noting that India has been climbing the charts on this chart, and I've tracked this chart for many years now. And India, every year, has climbed the charts to a point that it's the 5th country now on this list. And from an advantage view of a semiconductor company based in the US, it actually is really the second most important country because from our point of view, of course, US is the biggest market, but we're not really, we don't sell to China or Russia on this list, so in aerospace and defense market specifically, and Saudi Arabia doesn't really design systems. So India really is the second largest defense market from a semiconductor point of view, a company in the US. So certainly it's very important. Now, that was kind of the global defense budget. When you want to talk about India specifically, we want to zoom into the region first and see how the trend has gone in specifically in Asia and Oceania where this particular report covers, and that's the defense spending in this region also has been rising, where the spending is now up to $477 billion in 2017, at 3.6% higher than 2016, and a whopping 59% higher than 9 years ago in 2008. So this region itself is the second largest region in terms of military spending in 2017, and that regional dynamic, of course, motivates the countries in that region to also spend more, because if your neighbors are spending more on spending, it generally results in some motivation for the country to spend more on defense as well. So now specifically in regards to India, of course, as I mentioned earlier, over the last few years, the defense spending has gone up at an accelerated rate and has risen over the last 10 years more than 50%. This chart goes back to 2008, but if we actually go to 2007 and calculate till 2017, it's more than 50% increase in defense spending in India. Okay, so that was kind of the general global defense spending data. But what are some of the market dynamics that we see from our advantage view? First and foremost, big data is becoming more and more prominent in aerospace and defense. And with that big data comes the need for processing that data at the edge. And by the edge, I mean at the very end point where the data is being collected. So if it's a UAV, it's at the UAV. If it's a satellite, at the satellite. So that data needs to be processed at the edge. And because of the huge amount of data that's being accumulated, the need for machine learning and artificial intelligence is increasing. So it's becoming more and more of a focus area. And I will talk about those throughout this presentation. Also, another trend is the shorter time to mission requiring flexible solutions. If you're developing an electronic warfare EW application, your enemy comes up with certain algorithms. You have to come up and counter those algorithms quickly and update your systems. And so the flexibility of the systems that are being deployed is becoming more and more important to be able to respond to enemy threats across the world. Satellite payloads, the complexity is increasing, and increasingly there's a demand for in-system reconfigurability in space. So if I had to have you leave with one message from this presentation, it's this one right here. I know that may not be the case today in many of the applications you're addressing, but believe me, from our perspective, we can see a few years down the road and ability to reconfigure systems in space becoming more and more prominent. And you're going to see that becoming more important over the next few years. Radar common platform. There are a number of radar point solutions. The drive to develop a common platform for radar, I'll talk about that. And I'll also talk about supply chain and lifecycle management as well toward the end. So let me jump into big data and give you start by some examples regarding big data and how it kind of dictates some kind of a machine learning solutions. First of all, this here is a video surveillance example, and what you see is a US military drone. And this drone has cameras that are 1.8 gigapixel. So just kind of put that in perspective. The cameras that are in autonomous cars or your cameras are a few megapixel, 4, 8, maybe 12 megapixel cameras. You're talking about 1.8 gigapixel cameras, and there's 365 of these in each of the systems. So 365 cameras at 1.8 gigapixel. So the amount of data that this system accumulates is mentioned here in the bottom. As you can see, the daily footage is 8 to 10 petabytes, equivalent to 3 NFL seasons of HD video. Now, I assume most of you are not familiar with US NFL video. NFL, it's basically the football games takes about 3.5 hours. It's long. And you can see it equivalent to 768 games. Maybe a better example is it's equivalent to the Library of US Congress in 2016. Now, that's just one drone in one daily footage. Now, the US Department of Defense operates 11,000 of these drones. And the amount of data that gets, not just these drones, 11,000 drones all in all, but all in all, on average, you can see that could add up to hundreds of thousands of hours of footage. And then when you actually accumulate that over a period of time, that number blows completely out of the proportion. So this data requires some level of sifting through, learning, and be able to sift through it with machine learning and be able to deduce some surveillance-related conclusions. Now, so far, we've just talked about video surveillance and image and data, but there's another spectrum, and that's the electromagnetic spectrum and RF spectrum that provides even a larger amount of data. So if you take a look at the electromagnetic spectrum and you take the RF portion of that, it's a small portion of that spectrum. And then if you kind of map that to where the aerospace and defense systems care about, let's say across MILCOM, application, military communication, radar, or EW, and then you zoom into a very small band of that where a data converter, maybe a 4 gigasample data converter at 12-bit accumulates 708 terabytes per day. And then if you go to some of the more higher end data converters, you're talking about 5.1 petabyte per day of data. And if you want to really go crazy in the RF spectrum, you can look at this square kilometer array in Australia and across the world where radio telescopes look into space, and that amount of data accumulated by them are even larger. So machine learning also needs to be applied not just to video footage, but also to the RF spectrum as well. So when you think about machine learning for different types of data, there's similarities and there's some differences between these applications. You hear a lot about image and video types of applications, and there's a lot of networks that are developed that addresses image and video applications. Also, audio and language also is a key area of, that you hear about a lot. But RF is somewhat different in a sense that although it has some similarities in terms of its characteristics to the other types of data, there's complexities regarding its propagation. For example, RF goes through walls and it has a different propagation mechanism than the other types of data that you see here. And also, maybe more importantly, there's limited open data sets in RF. So there's a significant amount of efforts are being spent to be able to develop networks for this type of data. And there are studies that have shown that the deep neural networks do work for the RF spectrum, and those are being studied as we speak. So what does this mean? What this means is that machine learning is becoming more and more important, and it translates into certain applications in aerospace and defense, and also other markets. We at Xilinx have spent a lot of effort and investment both internally as well as acquisitions to acquire machine learning algorithms to address various applications, including automotive, video surveillance, and in many other different areas. But in aerospace and defense, you can kind of boil it down to 3 specific areas that we see: cognitive radios, cognitive radar EW, and onboard computer vision in applications such as drones. So the deep learning brings its own advantages in each of these areas, in each of these systems. So over the next few years, we think we're going to see trends in the aerospace and defense market that permeates to these types of systems that are being developed across the world. So a cognitive radio, just as a kind of a reference point, is basically a system that's aware of its environment, that it can monitor its environment and modify its performance based on its environment. It's adaptive and intelligent, and it can automatically detect the available bands, available spectrum, and switch to that. And also, if it's jammed, move to another band. So it's important for the cognitive radio to be able to adapt to the environment and find the appropriate band to operate on. Now, another, in this whole cognitive radio is applicable to a number of different systems in the aerospace defense industry, from manpack to handheld radios to vehicular, airborne, and shipboard radios. And a tremendous amount of processing is required to enable machine learning in these types of applications. And of course, those processing elements are things that we're focused on to make sure we bring out those capabilities in our current devices, as well as moving forward in the 7 nanometer, having even significant amount of more compute power to be able to do the machine learning algorithms. Now, when we talk about also cognitive radar and EW, similar to cognitive radios, it's important to have systems that learn their environment. You know, most of the world is fixed in terms of mountains and waters and buildings and such. Yet, today's radar systems learn their environment and forget about it a few milliseconds later. So a tremendous amount of cycles is wasted to relearn its environment every time a radar is operating in a certain area. So why not have radar learn its environments, knowing where the mountains are, where the trains are, where the buildings are, and only spend its cycle to detect specific things that you're looking for with that radar system. And be able to share that with other systems and other friendly radar systems around it. Now, while I'm on the topic of radar, and I wanted to bring up another trend, as I mentioned earlier, we see this becoming more of a trend, is the common platform. Radar common platform is realized through a development called the Multifunction Phased Array, MPAR. And what this is that you have a number of different radar systems that are operating. It could be weather radars, or could be the air surveillance or air traffic control radars. And each of these operate on their own and somewhat antiquated and needs to be updated. Yet, if we can have one common platform that addresses all of these, and this common module and common multifunction phased array type of a radar, not the old style radar, but the phased array radar, can replace these and be a lot easier to maintain in terms of the life cycle cost, in terms of the lower operation and maintenance cost, and increased performance benefits that comes with having a single platform across different types of radar systems. So we see this as becoming more and more of a trend in the future as well. Now, one of the key developments in the semiconductor industry that enabling the multifunction phased array is the advent of the programmable RFSoC as a disrupting element that enables this. So it used to be that in a radar, you used to have an SoC, some data converters, a bunch of data converters, and some FPGAs maybe. Now, with the one RFSoC that includes integrated data converters and SoC and FPGA in one system, in one chip, you really have a system on a chip that can address these types of applications in significantly smaller footprint at a significant power savings. So this is one of the key developments enabling the multifunction phased arrays. Let me now kind of switch to space, probably near and dear to the heart of the audience today here. Everything that I said so far is really applicable, of course, to the ground systems as well as systems in space, could be deployed in space. So all of the machine learning indications that I've been talking about so far are applicable to space. But let's now specifically talk a little bit more about a particular example, for example, in space. There are a number of satellites that are launched for image satellites. They capture images and transmit those images back to Earth. And if those images are not processed, you can spend basically the cycles of the satellite transmitting a cloud where it may not be useful as an indication to the ground station, whereas you really should be going through the data at the satellite, in the satellite, not underground, but on the satellite, being able to have machine learning that learns what types of images are important to the ground station and only transfer those data back to the ground station. So this saves efficiencies, power consumption, and other factors, and really improves the performance and efficiencies of the satellites that are up there in space. So it used to be that the satellites that you can see on the left, a traditional type of a satellite system, used to be deployed and merely capture data in space, but transmit to the ground for processing. These are becoming less common, as you could see on the right, more and more we see onboard processing capabilities in satellites. Satellites having processing capability at the edge, meaning where they are, and being able to process and have artificial intelligence to process some of that data and send only the things that are useful on the ground. And this brings complexity to the satellite, and this is where really the reconfiguration of the reconfigurability of the systems and satellites become more and more important, and hence FPGAs become more and more important. That's why you see more and more programmable systems being launched in space. So why would you want to launch programmable systems in space? It's really, for one thing, those systems, those FPGAs or programmables need to be able to have advanced commercial and defense capabilities, allows you to deploy those in space. So be able to do the function that you want, the payload function that's required needs to be able to be implemented. But maybe even more importantly, the on-orbit reconfiguration allows you to deploy these. Remember, these satellites becoming more complex, it's becoming more and more expensive to launch them, and the ability to fix bugs, update them on space become more and more important. I can tell you an example of a very, very famous space company that just recently launched satellites up in space in last February. And immediately after launching, they found bugs in the system. They were able to reload the FPGA and fix those bugs within hours in space. So this is being done. It's not a theoretical thing. In fact, in one of the slides, a couple of slides before, I had actually put down a YouTube picture right here, a YouTube video of showing the actual satellites and how they get updated in space. And then more importantly, these satellites can have different functions, have served different functions by dynamically changing the functions in space as well. So what's enabling these, again, is the development in the programmable industry that allows you to have more complexity at your disposal to be able to deploy these types of complex functions in space. And whereas a few years ago, in the older technologies, those devices were smaller. Now, with the new generations of the programmables, more complexity can be implemented in a programmable system, and being able to launch more processing, signal processing, and other processing capabilities up in space. For example, here at the 20 nanometer node, you're going to have an ASIC-like type of capability in a programmable system. And that's why you're going to see more and more in-system reconfigurability in space as we're going down the road. Now, so far, all of the technologies that I talked about are kind of exciting parts of the industry that we all like to follow, and we all like to be proud of some of the technological advancements in those areas. But the practical aspects of aerospace and defense market always looms large in regards to supply chain and availability of these products for many years. Now, it's every time a technology is deployed, you have some innovators, some early adopters, and then majority come in and take advantage of that technology, and then slowly that kind of goes away. Now, that's kind of a commercial life cycle of a semiconductor component. And many of the commercial type of companies adhere to that level of life cycle. But when you're deploying systems in space, when you're deploying systems in defense industry, you really cannot have a 5 to 7 year life cycle. You really need to have 15, 20 years types of a life cycle. So while you need all of these machine learning and artificial intelligence systems, you still have to make sure that those types of equipment that you're launching in space or in other defense applications are going to be there for many, many years, 15, 20 years life cycles. So that's very important. Coming down the wire, I wanted to close here, as I have just a couple of minutes left, with Xilinx is very proud of our presence here in India, and this initiatives around Build in India is at the heart of our presence here. We have a extensive R&D operations here. We have significant R&D development being done for our full product development here, IP portfolio, software, a whole host of developments are being done in Hyderabad. And the tools and applications are being developed here in India. We have a very close relationships with many universities here in India, and we work with many different, many of the different government agencies as well as commercial entities here to partner with them to develop, to provide components to enable built in the India systems. We have a number of partners, customers that enable that here in India. So with that, I will close the keynote. Thank you very much for your attention here. Thank you so much. Thank you.
Thank you, Yousef. I'd like to invite Mr. Rajesh Krishnan to give away a memento to Yousef.